Good morning. Myself Ram Gopal and my teammate Lahari. We have done project on resistance measurement and normalization circuit. So to measure resistance, like it cannot measure directly, like keeping the resistance, and we cannot expect direct value. We have to convert it into a readable quantity, let's say the voltage or current, and from that we have to estimate the value of resistance. So for that, like we in this project we have converted the resistance into the voltage. We measured it, and from that we tried to estimate the value of the resistance. So we have to convert into voltage, right? So we have used this instrumental amplifier, where in this circuit we have used three op amps US741 ICs with resistance all this. Here two op amps are in negative feedback, and one is a differential amplifier. One op amp is in differential amplifier mode. So here it has two input terminals and one output terminal, where one input terminal is grounded, and through the second input terminal we have given input signal of 1 sine omega t, amplitude of 1 volt, which is a sinusoid. And we have read the output voltage value. The output voltage here is 1 plus 2 R1 by R unknown into V input signal. Here R1, except R1, all resistance are fixed, like R4, R5, R6, R7 we have kept it to be 2.2 kilo ohms, because so that these values do not contribute to any gain to the output voltage. So R1 is the resistance we are going to change based on the measuring resistance range, and R3 here is the unknown resistance, where we have to keep the unknown load. So why we have used this differential amplifier is that basically this circuit can reduce the effect of noise on the output signal. That is the main motive to use this differential amplifier circuit. So this is the gain derivation. Output voltage equal to 1 plus 2 R1 by R unknown into V input. This is all the derivation that is done. So here it can be done keeping R1 as 1 kilo ohm constant and keeping unknown load there in place of R3. But the problem is, if the unknown resistance load, like unknown load is having a high resistance, like around 200k, 300k, 310k, 320k, let's say, then keeping R1 as 1 kilo ohm may not be like may not be preferred because of the accuracy issues. And if we have a load of 300 kilo ohm and some other load of 310 kilo ohm, there is a chance that the output voltage for both the resistance will be same, like approximately will be same, and we will be reading the same thing, that is 310 kilo ohm, 300 kilo ohm, both loads we are going to read the same voltage, which means we are going to think that both have same resistance. But that's not true. It has a difference of 110 kilo ohm around 10 kilo ohm around, which is not a very small value. So to avoid this resolution issues for large loads, for large resistance loads, with having only a small value of R1, we have changed the circuit, and we have modified the circuit slightly. Like we have classified the measuring ranges into three categories. One measuring range is from 1 kilo ohm to 10 kilo ohm with R1 as 1 kilo ohm. One measuring range is from 10 kilo ohm to 100 kilo ohm with R1 as 10 kilo ohm, and another measuring range is from 100 kilo ohm to 1 mega ohm with R1 as 100 kilo ohm. Here this circuit, like we are trying to see that the circuit can only like measure from the loads which have the resistance 1 kilo ohm to 1 mega ohm only. That is the only constant we are keeping now. So let's say we are fixing measure R1 for a given measuring range, right? So we have to expect the output voltage should lie between 1.2 to 3 volts amplitude. Means the output signal amplitude should be in between in the range of 1.2 to 3 volts. That is going to be the result of this type of classification. So if we have a unknown resistance, unknown load, let's say we know that its value is from 1 kilo ohm to 1 mega ohm, and we are measuring it with keeping R1 first as 1 kilo ohm. If the output voltage is greater than 3 volt, which means that the unknown load resistance having a resistance value less than 1 kilo ohm, which means our initial approximation is wrong. We cannot use the circuit. We can use the circuit, but we are trying to not use the circuit for the values less than 1 kilo ohm. That's it. If the output voltage is less than 1.2 volts, we can say that the unknown load resistance which we have is greater than 10 kilo ohm. Then we have to change R1 to 10 kilo ohm, and again we have to measure it. If again it is less than 1.2 volts amplitude, then it means that the resistance, unknown resistance, is greater than 100 kilo ohm, and we have to again change the R1 to 100 kilo ohm, and again we have to measure it. So for a unknown load which whose resistance we know to be 1 kilo, we know to be 1 kilo ohm to 1 mega ohm, it should lie in any of the three ranges. That's for sure. And we are going to measure the output voltage only if it is in the range of 1.2 to 3 volts. This is the process we are uh, following to measure the unknown load resistance. So this is the hardware simulation which we have done. Like we did not keep any LT spec simulations in this PPT. Like directly we have kept all the hardware simulations that are associated with this project. So we did not use like there is unknown load, and we did not change the three change checking. We did not check for every range is it is coming in between 1.2 to 3 volts or not. Like we have directly kept first R1 as 100 kilo ohm, and we used R1 as 1 mega ohm. We got the R unknown value as around 1035 kilo ohm. Now similarly we have kept R1 as 10 kilo ohm. Unknown resistance we used 20 kilo ohm and 91 kilo ohm. These are the values that we have estimated, that is 19.6 kilo ohm and 88.8 kilo ohm respectively. Similarly, we have done for R1 equal to 1 kilo ohm with the R unknown resistances as 6.8 kilo ohm and 2.2 kilo ohm, and we got around 6700 ohms and 2300 ohms respectively. So this is all the thing. Now coming to resolution, it means that for a what small change of resistance that the circuit can respond or can show the change is, it means the resolution. Here keeping R1 as 100 ohms, we have used R1 as 100, 104, 106. We can see that it is measuring very perfectly with a very very small error. And again the output, we can observe the change in output amplitude also, which means that the circuit is have a good resolution. But we cannot expect the same type of resolution for larger measuring ranges. Like we can see varying 2 ohms in this measuring range, that is here the measuring range will be 100 ohms to 1 kilo ohm. Changing 2 ohms we could get the significant difference in the amplitude. But if we are trying to change the same 2 ohms in the measuring range of 100 kilo ohm to 1 mega ohm, we will not see the same, we will not see the difference, like very perfect difference between those two output voltage amplitudes. This is the thing that resolution like decreases when we are going ahead in the values in the same measuring range, and also going to be and also it decreases when we are going to the next measuring range. That is the resolution point. Like we have increased resolution mm, by dividing the measuring ranges into three parts. Here there only we have improved resolution and accuracy a lot. Then this is the thing. And challenges we have faced is like we can see here the cursors. We have used cursors to measure the output voltage. Like we can see that the signal output signal has a bit significantly good bit. We like it is tough to estimate where to measure the amplitude, like from the starting point or of the width or ending point of the width or the middle point of the width. Like it is though it has around 0.05 volts, but for a larger uh, unknown resistance in a measuring range, like if you are taking a measuring range of 100 kilo ohm to 1 mega ohm, like this small changes will affect a lot when we are trying to estimate unknown resistance of 800 kilo ohms, 900 kilo ohms. Like these small 0.05, 0.01, these small voltages affect a lot, like show significant error in that when we are going of ahead, like in the measuring range. So to avoid this, we thought of using an Arduino, where we thought of giving a input DC input to the second terminal of 1 volt, and trying to measure and try to and trying we thought of trying to measure through the analog read, through the like we have we thought of giving through the output voltage of the amplifier to the Arduino through analog write, and then not of analog rate also directly. And like we thought of giving doing that, like we can see that Arduino has a very good as resolution, like can sense 0.001 volts also very clearly, and there won't be any ambiguity there. Like if we find this type of errors, we can say that we can see that we will measure the output voltage around 100 times and average it, so that if there are small changes also, those changes can be averaged, and it affects a very small, like the effect of on the output voltage will be very small because of that process of averaging. Through like this in Arduino itself, in Arduino code itself, we can do the calculation that we are doing the reverse calculation, right? Getting the output voltage, back substituting in the formula, and getting the unknown resistance value. Like this process cannot like need not to be done on the paper. Like it can be directly done in the code of the Arduino, and directly it can display the value of resistance of the unknown load. So this is the idea process and the conclusions, all the processes we have did, how we proceeded in the project, what can be done to improve the accuracy and resolution, like using the Arduino, using the computation that we are doing on pen and paper, through pen and paper directly in the Arduino code or the things. So now let's see the hardware part, where hardware simulation, live hardware simulations in the following video.